Hey everybody, welcome to our video on hydrocarbons and the carbon cycle. So the carbon cycle is incredibly important. It's really the basis of life as we know it, and understanding how the carbon cycle works helps us understand how life was balanced throughout Earth history. Also, the all-important oil and gas are formed as part of the carbon cycle. And of course, the resultant problem, global warming, is also part of the carbon cycle. So really, many of the most important things on Earth tie directly into the carbon cycle, so it's really worth understanding how this works. And this video will really be the first in our understanding or our exploration of oil, gas, coal, and other fossil fuels. So I first want to remind you that oil, coal, and natural gas are the three main fossil fuels and are all fall under the umbrella of hydrocarbons. And the key thing to never forget is that these sources of energy are basically derivatives of nuclear power. It's nuclear fusion that powers the sun, okay? The sun's rays come down and drive photosynthesis. And today we're going to talk about how that actually puts carbon into a reduced form, also known as plant tissues. And it's those plant tissues that ultimately die and are stored and heated to make the fossil fuels that we're all familiar with. Main point, all these fossil fuels are really just stored nuclear energy, and it's really plants and photosynthesis that are doing the storing for us. So fossil fuels are obviously really important. If we look at the energy balance of the United States, this is where we are in terms of total energy consumption. Petroleum and liquid fuels dominate. Natural gas dominates. Coal has been declining over the years, but is still important. And of course, we're happy to see that renewables are gaining steam, but they're really just getting up to kind of compete with coal and start to compete with petroleum. Main point here, fossil fuels are still incredibly important. They're not going away. It's really important to understand where they come from, how their supply might be limited or not limited. So we'll start out the video today and we'll look at the basic idea of what are hydrocarbons? What are these fossil fuels made of? Then we'll look at how hydrocarbons are produced in the carbon cycle. And so with some of that basic knowledge, we'll then go on and look at specifically how oil and gas are formed in the sedimentary environment. And we'll finish with the example of deltas, which are this incredibly important environment to store oil and gas. So hydrocarbons, as the name implies, are basically big molecules that consist mostly of carbon atoms bonded with hydrogen atoms. And it's really important to remember that the energy in a hydrocarbon is associated with this bond. When we burn these things, we break the carbon-hydrogen bond, and that releases the energy. So the more carbon-hydrogen bonds you have, the more energy you've got. And in particular, if you can pack a lot of these bonds into a small area, then that really gives you a great energy density. Now, hydrocarbons come in all flavors. So the shorter chain hydrocarbons tend to have lower vapor pressures, and they tend to be gases. So here we've got methane, propane, ethane, and butane. So these are all molecules that might commonly make up natural gas, which has a great energy density. Longer hydrocarbon chains tend to be liquids or solids. So gasoline typically looks something like this, maybe has 7 carbons. Diesel fuel is even bigger. And then when we get into the really long hydrocarbon chains, those are actually solids, like plastic and rubber. So the take-home message is, the bigger the hydrocarbon chain gets, the more solid you become. whether it's a more viscous fluid or whether it's an actual solid like plastic. So another key idea about hydrocarbons is that they come in different lengths and structures naturally. When you take oil out of the ground, you don't just immediately get gasoline. You get a whole variety of hydrocarbons, some short, some long, some very complex. And the whole idea of refining is that you literally take all of this raw material and you separate out hydrocarbons of different lengths. So you might have a bunch of gasoline, some jet fuel, and then you might have lubricants like oil, some of these longer hydrocarbon chains. Now, of course, as I just said, the size of the hydrocarbon chain and the density of those bonds really determines the energy density. And so if we look at this, methane is the most energy dense hydrocarbon you can have. It has 4 hydrogens for every 1 carbon. Okay? So what that means is you get to break 4 bonds and you get the energy out of 4 different bonds and you only produce 1 carbon. So you'll often hear it said that burning natural gas is better for the environment than burning oil, for example. And that's pretty much true because you get a 4-to-1 ratio for methane, whereas you get something closer to a 2-to-1 ratio for oil, okay? And the higher this ratio is, the more energy you're going to get by breaking bonds for the fewer carbon atoms. So let's look now at how hydrocarbons are actually produced in the carbon cycle. All right, where do these things come from in nature before we can burn them? So this plot shows the number of electrons in the valence state of each atom, in each element in the periodic table. And you might recall from previous videos that atoms that have 1 electron in their valence shell, or their outer shell, generally want to give this electron away. They want to share it. So we call them cations. Elements that are just missing 1 electron from their shell generally want to receive an electron. We call them anions. Carbon is right here in the middle. Its outer shell has 4 electrons out of a possible 8. What that means is that it's equally happy to receive 4 electrons or to give 4 electrons away. So I call it a switch hitter. It's happy to either give electrons or take electrons. And it's this versatility that ultimately makes it the building block of all natural materials, right? Most materials, including humans, including plants, are based out of carbon. We are carbon-based life forms. And it's because of this versatility. Carbon can bond easily with either cations or anions. And so the result of that is we commonly find carbon in 2 different states. We find it either in a reduced state or in an oxidized state. Okay? Carbon in a reduced state generally is acting as an electron receptor. It's taking electrons from hydrogen. So an example of a molecule in a reduced state is methane, CH4, right? It's the one we just looked at. In contrast, carbon in an oxidized state, we could think of it as giving its electrons away. In this case, it can give its 4 electrons or share them with oxygen. And each oxygen atom would like to have 2 additional electrons. So in that case, we make carbon dioxide. Okay, that's the oxidized state of carbon. So just to summarize that, you may remember from chemistry class, if you lose electrons, you're oxidized, and if you gain electrons, you're reduced. Leo the lion goes grr. Okay, so that's how you can remember these 2 things. And of course, we will be referring to this in general as organic carbon. Whenever you hear the word something is organic, it's not like a vegetable that didn't have any pesticides used. We more often, when we use the term organic, we are referring to carbon in a reduced form, right? So something like methane is an example of organic carbon. So we know that carbon can switch back and forth from a reduced to an oxidized state. How does it do this? And this is really the basis for the carbon cycle, is switching back and forth from reduced to oxidized. In order to reduce carbon, we have to put in energy, and that energy comes in the form of sunlight, okay? So what do plants do? They take carbon dioxide and water, and they mix them with they add energy from the sun, and they do the molecular chemistry process of photosynthesis. And as a result of that, they turn these two ingredients, they turn oxidized carbon into reduced carbon, okay? And that requires an input of energy from the sun. Now, this reduced carbon is effectively stored energy. Plants just acted like a solar panel, basically. They took photons from the sun, they used it to build this organic carbon molecule, and that energy is now stored in the carbon-hydrogen bond, okay? It's ready for animals to come along and release the energy. And that's exactly what most animals do. We, humans and other animals, undergo the process of cellular respiration, where basically we eat these organic carbon molecules and we burn them. And as a result, we put out carbon dioxide and water, okay? And we get from that, we get energy, basically, okay? So that's the carbon cycle in a nutshell, the switching from reduced form back to oxidized form. Going to reduced requires energy input. Going to oxidized releases energy. All right, so let's zoom out from the molecular level and let's look at this in terms of the Earth system as we know it, okay? Where is this oxidation and reduction happening in the Earth system? Well, why don't we start here with photosynthesis? Plants are taking carbon dioxide out of the atmosphere as photosynthesis, okay? And then when those plants die, they go into the soil, okay? Here in the soil, bacteria eat them, and they undergo cellular respiration. And that is a form of oxidation. They're oxidizing that carbon, and they send the CO2 back to the atmosphere, okay? So that's the basic carbon cycle. Plants do photosynthesis, bacteria break it down and do respiration, and oxidize that carbon back into the atmosphere. Now, if some of that carbon doesn't get oxidized by bacteria, it will get stored. And if it gets stored and buried as rock, it becomes a fossil fuel, okay? Literally, the system siphons off some of that reduced carbon and stores it as fossil fuels before it can decay. And of course, we all know the rest of this story. Humans come along, we get the oil, we get the gas, and we burn it in power plants or in our cars, and we oxidize that carbon and we send it back to the atmosphere as CO2. So humans have kind of come in and added this piece of the carbon cycle where we are very rapidly sending CO2 back to the atmosphere. And of course, just for an example, we do that right here at Middlebury College, right? In the center of our campus, we have a biomass plant where literally truckloads of organic carbon arrive each day, and they are burned inside a huge furnace, and we use that heat to make hot water and steam to actually heat and power our whole campus, okay? Now, the reason that people think the biomass plant is better than, for example, burning oil in a central plant is because the idea is that biomass comes from trees. It doesn't come from fossil fuels. And the trees are going to be replaced more quickly by regrowth. So just to flick back to this slide, if we burn the trees right here in our biomass plant, and we send that CO2 back to the atmosphere, that tree can regrow pretty quickly. And so we can kind of tap into this part of the carbon cycle if we use a biomass plant, as opposed to burning fossil fuels, where that carbon may never end up getting back into the buried location where we found it. Okay, great. So that wraps up what are hydrocarbons and how are hydrocarbons produced as part of the carbon cycle. So you now know kind of the basic theory of the carbon cycle. So now let's zoom in on this piece of the story where we're actually storing organic carbon in making oil and gas. Okay? Now there's 3 key steps in oil formation. The first step is to bury the organic material without letting bacteria decompose it, okay? We just talked about how most organic material gets eaten by bacteria right away, and that CO2 goes back to the atmosphere. In this case, we need to bury it without letting it decompose. And the key to that is that we need an anoxic environment, right? Most bacteria and other organisms need oxygen to burn the organic material, to do cellular respiration. If we deny them oxygen in an anoxic environment, then they won't be able to break down the organic carbon as fast, and we'll have a chance to store it. Okay, so first we're going to bury, and the second step is we're going to convert that organic debris into hydrocarbons by heating it, okay? Hydrocarbons are relatively refined molecules. It's, a molecule of methane is not the same as a piece of tree bark, okay? We have to break down the cellulose in that tree bark using heat in order to make it into a hydrocarbon. So we're going to do some heating of the organic material, and then the third step is we're going to trap that oil and gas in some geologic rock units so we can come along and get at it later. All right, so let's look through this a little bit here. Where could we bury organic material under some anoxic conditions? The best place is basically an ocean basin that is fed by a river system. All right, so what do I mean? Here's an ocean, here's the land, we've got a river coming in here, and we've got some very deep water. And the deal is this: oxygen doesn't circulate very well in the water. It doesn't mix well. So deep water tends to be very anoxic, okay? Not much oxygen gets down there, and there's a huge demand for oxygen. So if we can put organic material down onto the bottom of the ocean in the anoxic conditions, it won't be able to decay, right? And then moreover, we can add in some rapid sedimentation. We can quickly bury that organic material with other sediments, okay? And so we can create a situation where the rate of organic input actually exceeds the rate of decay, right? We're piling up more organic debris faster than it can decay, and then we can start to bury it and store it. And a common rock is going to be a deep water shale. This is a common rock where you might find forming on the deep ocean floor with lots of organic material in it. And so, just to reiterate, a couple more reasons that this ocean basin is near shore is such a good environment for oil and gas. One is that we have a lot of sediment coming in from the rivers. These rivers are delivering sediment really fast, which means we can rapidly bury a lot of material. Also, we're getting a lot of carbon from terrestrial sources. these rivers are literally carrying a lot of organic carbon from soils and from trees, all throughout the interior of the continent. And they're also bringing with them nutrients, phosphorus, nitrogen, iron. These nutrients can drive productivity of phytoplankton in the ocean, and those plankton can then die and actually settle down to the ocean floor as an additional source of organic material. So what's a real-world example of this? A great example is the Mississippi River discharging sediment into the Gulf of Mexico. Here comes the Mississippi. It's draining literally half of the United States. It's a huge river. When it comes flooding into the Gulf of Mexico, it's dumping all of this sediment, okay? It's bringing organic material, it's bringing sand, and that sediment is literally dispersing itself onto the bottom of the ocean floor. Now, once that sediment's on the ocean floor, we can consider the second step, and that is conversion into hydrocarbons by heating, okay? As the sediment piles up on the ocean floor, it acts like a blanket or an insulator, and the temperature starts to rise, okay? So the more deeply you bury the sediment, the hotter the temperature gets. And we start to cook off volatiles. We drive off oxygen, we drive off nitrogen, we drive off water, and we start to break bonds. We take our bigger plant tissues, we break down the organic molecules, and we start to restructure them into hydrocarbons. Now, one essential thing is that oil tends to form between about 60 and 120 degrees Celsius, and gas tends to form between about 120 and 200, okay? So gas is basically, those are smaller hydrocarbons. They're more refined. We actually have to cook them to a higher temperature in order to break them into those smaller gas molecules and make them more mature. The other thing to notice here is that the exact temperature, the exact depth at which you might start to make oil depends on the thermal gradient. If you're getting hot really quickly, like this orange line, then you may start to make oil as shallow as 1 kilometer. But if you're getting hot slowly with depth, then you might have to be as deep as 3 kilometers before you start making oil. So it's the steepness of this thermal gradient that really determines the depth at which you might start to make oil or gas. All right, so now the third step is to actually trap the oil and gas in some geologic formation. If we don't effectively trap the oil and gas, it just begins to escape. And if you've ever been to a beach and seen tar balls or oil film on the beach, such as this example of tar on the beach in Santa Barbara, what you may have seen is actually oil and gas that actually escaped naturally from the deep subsurface. They were not successfully trapped, okay? So we're going to need to trap them in order to extract them later. So we need 3 rock units to do this. We need a source rock, a reservoir rock, and a cap rock, okay? A good source rock is an organic shale, like we talked about, something deposited on the deep water ocean floor. A good reservoir rock is a sandstone, and often limestones also. These contain a lot of pore space. That's open space between the grains of sand where we can actually trap liquid oil and gas. And then the final thing we need is this cap rock. This needs to be an impermeable layer, okay? It needs to be impermeable so that oil and gas cannot pass through it, like a seal, right? And then if you have this sealed cap rock, it's going to trap the oil, which is trying to migrate upwards and escape because the oil is hotter and less dense. So it's always trying to migrate upward and escape. and we need this cap rock to keep it in place. So a cool real-world example of this is the Tupi oil field in offshore Brazil. This is kind of a neat example because this was a huge oil find that wasn't discovered until 2006. And the reason is that it had some oil-bearing sandstones that were actually buried beneath almost 5 kilometers of salt, okay? This incredibly thick salt layer, and was very difficult to drill through. It was very difficult to do seismic imaging, but of course it was acting as an amazing cap rock to actually trap oil and gas down in these sandstone layers beneath it. All right, so now that we know a lot of the basics of the carbon cycle and of oil and gas formation, I want to wrap this all up with the concept of deltas. And deltas are a type of sedimentary deposit that forms where rivers flow into oceans, okay? And the classic example that we already looked at is the Mississippi River Delta. And of course, these are relevant because we already talked about it's the place where rivers meet ocean basins where we really have produced optimal conditions for oil and gas. And let's look at how deltas even further optimize that. Here's the deal. Deltas consist of big rivers coming down, and where they meet the ocean, they basically can no longer carry sediment. As that river water hits the ocean, it loses its energy, it loses its ability to carry sediment, okay? So it drops the sediment here. And as a result, the sediment piles up, the river has a hard time deciding which direction to go, and so you end up with these really crazy distributary channel networks. The river starts to braid out and split into all these different channels as it's kind of trying to find its path through this big mass of sediment that it's dumped at its mouth. So here's the real world example of that, Mississippi River Delta. Here we are looking out to sea. Okay, so this is looking south out to the Gulf of Mexico. And then here's a view from space. Here's the main channel of the Mississippi coming down. And then here's some of its many distributary channels where it's splitting off and it's delivering sediment out to all these different parts of the Gulf of Mexico. You can see how muddy the water is here, all that sediment and organic material coming in. Now, one key idea about deltas is that they actually prograde over time. And this is a complicated concept, but here we go. Here's the ocean basin. Here's the river coming in here. Keep in mind, as soon as that river hits the ocean, it has to drop its sediment, okay? So what happens is we keep depositing sands right here at the shoreline, okay? Now, as we deposit sands, basically they pile up and they end up being above the water level. And so what happens is that the river is then forced to continue out even further to sea. And the front of the delta is actually going to migrate outward in a process called progradation. So if this is what the Mississippi Delta looked like 20 million years ago, here's what it looks like today. As the sediment piled up, the river kept advancing further and further out over it, dropping more and more sand, and building this huge delta complex, which is mostly made of coarse sand. And of course, today the river is literally tens or even hundreds of miles south of where it was 20 million years ago. So it's basically advancing out over its own pile of sediment. Now, the reason this is ideal for oil and gas is that what we've now done is we've put coarse sand out over organic shale, right? 20 million years ago, we were depositing muds and silts and shales and organic material, all out in the deep water. Today, those muds in that organic material, the shale, is actually buried by several kilometers of sand. Guess what? Here's our source rock in the organic shale. Here's our reservoir in the coarse sand. We've got a perfect setup to produce oil and gas and store it in our coarse sand units. Now, and I just went over this, if we can come up with a capping unit, maybe we could rise sea level for a couple million years and put some shale down, or maybe we could evaporate the whole basin and put down some salt. If we can cap this with shale or salt, then we've got our perfect setup of source rock, reservoir rock, and cap rock. And so it's because of this process of delta progradation that deltas are ideal locations for the formation and the storage of oil and gas over time. Okay, so to summarize this video, we've covered a lot of ground. Here's what we've talked about. The energy in hydrocarbons is stored in the carbon-hydrogen bond. The more dense your carbon-hydrogen bonds are, the more energy you've got. The carbon cycle lets us take carbon from a reduced form to an oxidized form. It's photosynthesis that causes reduction, and it's cellular respiration, or burning, that causes the oxidation. Fossil fuels are created when reduced carbon is basically siphoned off the carbon cycle and buried before it can decay, usually buried in an anoxic location. Now, oil and gas are produced in 3 steps. First, we bury the carbon in an anoxic location. Then we convert it into hydrocarbons by geothermal heating. And then we trap it below some impermeable layer. And we wrap all that up by talking about why deltaic environments, like the Mississippi Delta, are ideal places for forming oil and gas and storing it. Thanks for following along. Here's a couple concept questions, and see you in class to review all of this.